Okay, gang, back with part 2 of our screener on free body diagrams. Let's pull this box at an angle. We have a box with a mass of 10 kilograms. The weight's going to act down with a force due to gravity of negative 98.1 newtons. That's 10 kilograms times negative 9.81 meters per second squared. We're going to use the force, Luke, and we're going to apply force of 100 newtons, okay, on this box, but we're going to apply it at an angle above the horizontal of 30 degrees. This can be broken up into components. We can break forces into components like we broke up other vectors into components. Okay, Fax and Fay. And we're going to use exactly the same types of formulas. Any vector times the cosine of the angle it makes equal its x. And any vector times the sine of the angle it makes equals its y. So, the normal will be reduced by whatever we are pulling up on this box. Okay, the acceleration depends only on the x force. All we're going to reduce is the amount of force acting on the floor. The floor has to push back up with less force because we're pulling up slightly. Let's try an example problem. A man pulls a 40-kilogram crate across a smooth, frictionless floor with a force of 20 newtons that is 45 degrees above the horizontal. What's the net force acting on the sled? Or on the crate, it should be. That's a typo. Okay, F net equals Fa cos theta. So 20 newtons times the cos of theta, 14.14 newtons of net force. Okay, what's the crate's acceleration? Well, that's again F net over m equals a, about 0.35 meters per second squared. What would happen to the acceleration? The box were pulled at a greater angle or a smaller angle. Well, you know how that's changing. As you get to a greater and greater angle, more of the force will be applied up and less of the forward will be applied forward. And in a smaller angle, more of the force is applied forward and less of the force is applied up. So in fact, the best way to apply a force is perfectly horizontal if you want the crate to move horizontally. Okay, the greater the angle, the horizontal component would be smaller, making F net and the acceleration decrease. Okay, so let's push now at an angle. Again, same kind of box, 10 kilograms. There's the weight. Now we're going to push down on the box at 100 newtons down. Why you would want to do this, I don't know. But you could. That force can be broken up into components, same way we've done in the past. Okay? Now, what's happening in the vertical dimension? Because we're pushing down on this box, we're actually adding to the weight, and the normal force would have to be greater. Okay, the applied force in the y direction is now negative 50 newtons. When we add that to the weight of negative 98.1 newtons, the sum of the forces is 0, so therefore the normal force has to be positive 148.1 newtons. Normal force is increased. That's one of the reasons you never want to do this, because you actually, with increasing the normal force, increase the friction force. Okay, what's happening in the horizontal? We know Ax is equal to Fa cos theta. So 86.6 newtons, and since it's frictionless, the Fax is equal to the net, and we can calculate the acceleration of this particular box. Here we go, a girl's pushing a lawnmower, 30-kilogram lawnmower with a force of 15 newtons, 60 degrees below the horizontal. Assuming there's no friction, what's the acceleration of the lawnmower? F net is equal to Fa cos theta, 15 newtons cos 60 degrees, 7.5 newtons of net force. A equals F net over m. You can calculate that the acceleration of that particular lawnmower would be 0.25 meters per second squared. What could she do to maximize her acceleration? Well, if she wanted to make the thing go faster, she could push more horizontally. The closer you push to the direction of motion, the greater the acceleration you get in that direction of motion. The best way to push anything is in the direction you want it to move. All right, well, that finishes that screen R, and we're going to do lots more forces problems. Great job, gang.